Hello everyone. We're now going to the second stage of CDS pricing, which what we're going to do is we're going to use a full-blown model to price a CDS. So we're going to use the model in this paper here. Okay, we're going to have to specify more assumptions, but we will get in the end a very precise price for the CDS that we can use for trading. Okay. This model may look a little bit complicated, but actually we already have all the ingredients we need to price this new CDS. Okay, so what we need is just the following. So going back to the figure that we had up here about how a CDS works, this one. So if you look at the CDS, you can actually think of this pretty much like the underlying bond itself. So the CDS will pay a constant cash flow over time while the bond is alive. So think of this as the bond coupon. And then it will pay in the other direction a value which is the loss given default, or 1 minus the recovery rate if default happens, right? So we can price this CDS contract just using two ingredients that we already have. The first one is what we did for pricing the actual bond. So if you go back to this chapter on pricing a bond, what we did is we decomposed the bond cash flows into the good state cash flows, the coupons, and the default case cash flows. And then we apply the probabilities of reaching those states, the risk neutral probabilities. Recall, we have to use risk neutral probabilities here, and then we multiply the cash flows by those risk neutral probabilities, and then discount the cash flows at the risk-free rate. And the price of the bond was just the sum of all these terms, right? So that's exactly the same thing we are going to do to value the CDS. So where is that? Here. Where was I? CDS here. So that's exactly the same thing we're going to use here. We will just have to be careful that some cash flows go in one direction and the other cash flows go in the other direction. So some will have a positive sign and the others will have a negative sign. And the second ingredient that we will use is has to do with the fact that this is still a swap. This is still two legs going in opposite directions. So the approach we will use is the same as we used to price an interest rate swap, meaning we will define the price of the credit default swap, this amount here, by making these values such that at time 0, at the beginning of the credit default swap, these two legs have the same value, right? So again, essentially, the model will look complicated, but don't be scared, because what we're doing is just the same thing we did to price bonds, and plus the same arguments we use to price an interest rate swap. Okay, so let's see how to do this. All right, we are going to use exactly the same probabilities of survival that we defined before. This lambda is the hazard rate, again risk neutral hazard rate. Let's start with the fee lag. Okay, so the fee lag, the present value of the fee lag is just going to be the present value of the payments that happen while the underlying bond is still alive. Okay, so we will pay a fee that is given by the spread of the CDS, which is in the end what we want to determine, times these factors here. So to understand this, actually, since this S is a constant, move this inside the summation next to this delta Ti, okay? And this will be, so this S is an annual figure, and then this delta Ti just adjusts for the payment frequency. So if the payments are, say, twice a year, semi-annual, this delta Ti will just be 1/2. So you would divide the annual spread by 2, okay? And that would be the amount you would pay every 6 months, times the probability of surviving until that period, and then discount, this is the discount factor at the risk, using the risk-free rate, so discount that back to today, okay? And then you add up all the fee payments that the CDS specifies, so from the beginning until the maturity of the CDS, okay? So that's the present value of the fee lag, okay? Now we just one more detail. Like we saw in the first example we did on CDSs, the contract may specify that if default happens, you have to pay the accrued premium from the last payment until the actual default date. So if the contract specifies that, the present value of the fee lag is what we have before, so this term here, plus a little bit, which is that part of the accrued premium. Okay, so the details of this are provided in the paper, but intuitively what we are saying here is that this is the probability of surviving until the beginning of the period and then defaulting over the whole period. Okay, so we decomposed this expression here when we did the bond pricing chapter. Okay, so go back and make sure you understand why these probabilities are here. Again, this is the probability of defaulting only in this particular coupon period. And then what this is intuitively, what this is doing is that on average I will default in the middle of the period. Okay, in reality I may default in the beginning, in the middle, in the end, and at any point in the period, but on average I default in the middle. Okay, so this is that, again, that term, and then this is the part that accounts for accrued interest. So if the contract specifies accrued premium, not interest premium, then you need to add this term here to the present value of the fee lag. Okay, this whole thing, if you put the S is constant, if you put that in front, you can call the whole thing that is left RPV01, which stands for the risky present value of an 0.1, so of a 1 basis point. Okay, this can be written in this more compact way, which you see here in this line, where basically what you put here, this 1, is an indicator. Okay, so this is either 1 or 0. Okay, and it will be 1 if the contract specifies accrued premium. Okay, so if that is the case, this term is on. If the contract does not specify the accrued premium, this is 0, so this part disappears and you are left with just this simple version that you have here. Okay, all right, so that's one leg. Now let's look at the other leg, the default leg. So the one that only happens in case of default, right? So as we know, if default happens, what the insurance company, if you will, has to pay to the protection buyer is 1 minus R, right? So 1 minus the recovery rate. So basically what we want to determine is the present value of that term when it happens, okay? So these are the probabilities of surviving until the beginning of the period and then defaulting over the period, okay, which again can be written in this form here as we discussed before, right? And then this is the discount factor from that period back to today, right? And then therefore if you add up all these terms, you get the present value of the default lag. Okay, so this is the part where we are using just the techniques that we used to price the bond. Okay, now the second part is we're going to use the technique of pricing an interest rate swap, for example. So basically what we do is we define the price of the swap, be it an interest rate swap or now a credit default swap, such that the two values have this, the two legs have the same value at the beginning. Okay, and that's what we have here, right? So basically if we put the two legs equal to each other, we get this equation, and this is an equation to solve for S, for the price of the credit default swap, right? So let's see an example. So let's suppose we have a 1-year credit default swap with quarterly payments at every quarter. Let's assume a recovery rate of 40%, and let's assume that the default intensity is constant at 1%. Okay, and we assume that premium accrued is due if default occurs between payment dates. So it's the big expression where you have to account for accrued premium. Let's say that interest rate, the risk-free interest rate is flat at 5%, and this is we're going to work with continuous compounding, so this is a continuously compounded rate. And let's compute the CDS spread, okay, the price of the CDS, if you will. Right, so I did this with a Excel sheet that I will make available for you to look at, but let's go over it here. So basically what I'm doing here in this file is just to use the formulas that are in the handouts as I just showed you. Okay, so here I entered the recovery rate. This is just the time. Okay, so the delta TI in years, quarter in this case. The interest rate, I assume flat at 5% for every period. So this is the discount factor. Again, the rate has continuous compounding. Okay, so here now I am computing the probability of default. So recall that the probability of default comes from the probability of survival, okay, using that exponential of minus the integral of lambda. So I'm putting the same lambda constant through time. This is the lambda dt that you see in the integral, and then if you add up the lambda times dt, you get the integral. Okay, and then the exponential of minus that is the probability of survival up to that moment. Okay, and then to get the probability of default, we have to do that transformations we just discussed. All right, so now these are the two legs. The fee leg, the one that you pay the fee while the bond is still alive. Okay, this is that first term that you have in that big expression in the handouts, one for each period, and then this is that second term that has has to do with accrued premium. Okay, and that's again one for each period. And then we call risky present value of an O1 the sum of that big sum, that big expression you have there. All right, so this is one part of the CDS, the part of the fee leg. Then what you have here is the second part of the CDS, the default leg. Again, this is directly the expression you have in the handouts, this term for each period, and then the sum of all these cash flows gives you the value of the default leg. And then the spread of the CDS is just the value that makes these two legs equal, or I can solve it for it like this, just dividing the RPV01 by the value of the default leg. Okay, or actually vice versa, the inverse of this, right? And that gives me the CDS spread, 60 basis points in this case. Now that we know how to price a CDS, there are a couple of interesting things we can do with that. So the first one is to estimate what are the default rates implied by market prices. So basically what we're going to do is very similar to what we did in fixed income when we estimated the term structure of interest rates. We used observed market prices to infer the interest rates that were used to set those market prices. So that's exactly the same thing we're going to do here. We're going to use the observed CDS prices in the market, or CDS spreads, and infer from those market prices what are the probabilities of default. Okay, so for example, suppose I have these two CDS contracts trading on the market. A one-year CDS is trading at 60 basis points, which is this CDS we just saw in the previous example. And I also now have a second CDS for 2 years trading at 89 basis points. So what I'm going to do is I'm going to use the first CDS to estimate the default probability over 1 year, or more precisely the default intensity, the lambda, over 1 year. Okay, so this is the previous example, so I already know what I should get from that. I should get the number I used in the previous example, which is 0.01. But I mean, in reality, I would not know what would this number. So I would have to estimate what would be the lambda that would make my model give me a price equal to the price I observe in the market. Okay, and then I would move on to the next CDS. So the next CDS allows me to have an additional year, and the spread is 89 basis points. So I would use the lambda from the first CDS and then estimate the lambda over the second year. That would make my model give me this market price. Okay, and keep going through this iterative process, which, as you know, is called bootstrap. Right? So let's see how to do this in Excel. I'll go back to the other file here. So this is the previous file again, where we determined the spread of that CDS. Now let's go to this case now where I'm looking at the market prices and infer the lambdas. So what I have here is exactly the same structure. It's exactly the same formulas we have seen before. The new thing now is this part here where I am extending over the second year. So I'm going to show you how I did this to determine the second lambda, okay? And you can see from that how we do this for more periods, for whatever number of periods. So I have the first CDS already built in here. It ends here, and now over this, when I switch to the second year, where I'm going to use information from the second CDS, I am going to allow for a different lambda. Okay. In the beginning, I don't know what should be this number, so since I would estimate 0.01 for the first year and I don't know what's coming next, I would say, well, let's keep it at 0.01. So notice that I keep this flat lambda for the full next year. Okay. The formulas again are exactly the same as I described before. So the fee lag is computed in the same way. Obviously now I am adding all these numbers because this is the CDS for 2 years. Here the default lag, again, the same thing. It's the sum of all these terms here because it's a 2-year CDS. And now what I have here is the spread that comes from my model, determined like I did for the 1-year CDS. And what I have here is the market price, what I observe in the market. So this is this constant number. And here it's the difference between the two. Okay. So I'm going to use the usual trick. So I'm going to use solver to make that difference be 0, right? By changing what? By changing the lambdas, right? This lambda here. Notice that all the following lambdas are linked to the first lambda, so I just need to change that single lambda there, right? So I solve this and I get a solution, okay, and it converged to this 0.02, okay? So this is the lambda for the second year, all right? So notice the second CDS is using a 0.01 lambda over the first year and then a 0.02 lambda over the second year, right? And that's the result I need to match the market, all right? So going back to the handout, we did this, okay? So why do I want to do this? Well, now I have a term structure of default probabilities, or default intensities and default probabilities for this firm, right? So now I can use this information to price any new contract issued by this firm, any new CDS or any new bond issued by this firm. Okay, so that's what we're going to do here. In this example, we're going back to that example we have seen before about the bond issued by this corporation. And now let's apply this new concept. So let me open this this new Excel file here. Again, this will also be available in the course webpage. The video is not refreshing. Hold on. Okay, so now it's in the right position. Okay, so this is the file you will have in Moodle. What we are going to do now is the following. We are going to use information from the CDS market on this same company, EDP, to price the bonds issued by this corporation that we have used before. So basically, we are going to see if we can we can come up with a reasonable price for this bond using information from the CDS market. Okay, so this is the CDS. The CDS price is trading on this firm. Okay, we get this from Bloomberg. And over here you get the prices that we're going to use taken from this screen. Okay? So the 1 year, 3 year, 5 year, 7 year, and 10 year CDSs have these prices that you see here, right? So that's one input we need, CDS prices. We are also going to need risk-free rates. So we're going to the swap market, the interest rate swap market, and get the swap rates from that market. That's what you have here in this this column here. Okay. We do something similar to what we did when we did the bond pricing. Namely, we go from the swap quotes to 0 rates. Okay, I'm not going to go through the details in this part here, but this is just an intermediate step that we do here in a quick and dirty way using this Excel sheet that does this conversion from yield to maturities to 0 rates. Okay, so in the end, what I have are these discount factors from the swap curve, so risk-free rates. Here we do an additional step which we have not done before, which is the following. I am going to have to use discount factors for a lot of different maturities, and I would either have to build a lot of interpolations by hand almost, or a quicker way to do that works very well is just to estimate a function over these discount factors that I have here. Okay, so what we do here is a polynomial of the 4th degree here, and as you can see, it matches almost perfectly all the discount factor curve that you see here. So instead of doing linear interpolations one at a time, I am basically just going to use this function whenever I need to get a discount factor, right? Okay, so now let's estimate the default rates or the hazard rates. Okay, so this is a big sheet. It does not fit all in here, so let me give you the overview of what's going on here, and then you can look at the details on your own. So there are inputs here marked in orange. So these ones here are the ones we just saw about the discount factor. So these are the coefficients on the polynomial. So whenever I need to have a discount factor, for example, like here, I'm going to use that expression, that polynomial with these coefficients. Okay. So the interesting part now is actually this one here of the CDS. So these are the CDS prices I'm going to use that came from the first sheet we saw. And what I have here now are the CDS prices given by my model. Okay. What I want is to find the lambdas that make the difference between the market and my model as small as possible. Okay. So what are these lambdas that you see here? These are the lambdas that will apply for each of these periods. So this will be the lambda that applies for 1 year. This will be the lambda that applies for the additional 2 years between 1 and 3. This will be the lambda for 2 more years between 3 and 5, and so on. Okay. So where does that come in? This is again the same structure that we have seen before, but now it's longer. Right. So as you can see here, these lambdas are changing when the previous CDS ends and the next CDS begins. Okay, so this will be the lambda from 2 to 3. Right. What I get here are the CDS spreads from my model. Okay, computed exactly as we have seen in the previous small example, like that toy example we saw before. Okay, and these values are coming to here. Okay, and again I'm picking the lambdas that minimize the difference between these prices, and I can actually do this in an efficient way in the sense that here I compute the difference for each CDS, and then I add up all the differences, and I just apply the solver. I can push the solver here. Oops. So, nope. Data solver. So what I'm doing is I am minimizing this cell here by changing at once all these cells here. Okay, and this works reasonably well. It immediately gives me all the lambdas in just one single step, right? And that is the result. These are the final lambdas, and they are also plotted here. So what you can see here is the hazard rate for this firm, estimated from the CDS market as a function of so it's the hazard rate as a function of time. Okay, so this step function that is implied by these lambdas here. All right. Okay, so now that I have the probabilities of default for this firm, I can price any other security issued by this firm. So what we're going to do is we're going to price the bond issued by this firm using the probabilities of default estimated from the CDS market that we just saw, right? So this is again exactly the same information that we had before when we priced this bond. Same data, same bond, everything here is the same. The only thing that now changes are these probabilities, right? So these probabilities of survival come from what we just estimated, right? So actually this is coming from here on the right. I repeat the lambdas that we obtained in the previous calculations and estimate the probabilities of survival. But again, here there is nothing new, right? These are the probabilities, or the lambdas, sorry, the lambdas that come from this previous estimation we did in the previous sheet. Okay, so nothing new so far. This is the probabilities of survival, the probabilities of survival that I get from the CDS market. And then I apply the usual formulas that we used, like that tree framework we used to price a bond, right? So the price of the bond, the full price, is just the sum of all those cash flows, the cash flows in survival plus the cash flows in default, and everything is multiplied by the corresponding probabilities that again come from here, which again come from the CDS market, right? So if I add up all that stuff, my estimate for the dirty price, the full price of the bond, is 114.5, okay? The accrued interest is the same as it was before, like when we did this initial example. Nothing changes here. So the clean price is just the difference between the two. And this is the one I compare with the market, right? So my guess for the value of this bond is 113.51. And I look at the market, it is trading at something very close, right? 113.705, right? So a nice result. Obviously, I would not expect to find a big difference. In reality, we should not expect to find very big pricing errors or arbitrage opportunities. So it's nice that I am getting a price that is very consistent with the price I actually observe in the market for this bond. Okay. So let's go back to the handout. So one last thing we're going to do here with CDSs is to mark to market an existing CDS. All right. So the idea here is that I have a CDS that was initiated sometime before. In the meantime, market conditions have changed, and now this CDS that started with a value of 0 may have a positive or a negative value to me. Okay. So if I want to unwind the CDS, if I want to cancel my contract, I may have to pay or receive some money to the counterparty. And what we are doing now is determining exactly how much do I need to pay or how much can I receive to end the contract. All right. So the idea is the following: the mark-to-market value of the contract, so an amount in dollars, is going to be given by this expression that we have here. So V is the notional of the contract. This risky present value is that function we have defined in the previous section that basically just gives me the value of all the spreads that are going to be paid, the present value of all the spreads that are going to be paid in the contract. Sorry, let me rephrase that. It gives me the risky present value of 1 basis point. So when I multiply that expression by a given spread, it gives me the value of all the spreads that are going to be paid. Now the new thing here is this difference that you see here, right? So S0 is the spread of the contract that I have already, that I am trying to value, okay? And ST is the spread that I would get if I went to the market to get an equivalent contract right now for the residual maturity of the contract, okay? So intuitively, it's probably better to see this with an example. Suppose the following. So suppose some time ago, we're going back to this. We're going back to this simple example that we have here, right? If I look at the market right now, and I want to buy protection on this underlying firm, these are the prices I get. So for protection for 1 year costs 60 basis points. Protection for 2 years costs 89 basis points. Okay, so this is the market right now. But let's assume that some time ago I bought protection on that same underlying for 70 basis points, okay? And at this moment now, this CDS that I bought sometime in the past still has 2 more years to go, right? So what I can do now is to compare this CDS that I have with what I would get in the market right now. And again, if I go to the market right now and I want protection for 2 years, I need to pay 89 basis points. So basically what I have is something that is good, because I am getting protection for the next 2 years, just paying 70 basis points. And this is good compared to the market. If I was going to buy protection right now, I would pay more. I would pay 89 basis points. So what I have is good. It's a good contract. It has value to me because I'm paying too little for protection, basically. So I should expect expect a positive mark to market, because this current price in the market right now is higher than the price that I have in my current CDS. So this difference will be positive. Okay. So now this is just doing straightforward calculations. This risky present value of 0.1 is the number that you can get from that Excel sheet I just showed you. It's right there, getting that and then replacing it in here, using for ST using 89 basis points, for S0 using 70 basis points, and then the notional is 10 million. Doing all that multiplication, you would get a mark to market of $35,500. Okay, so the contract has a positive value to me, meaning if we, me and the counterparty, if we agree to terminate the position today, I would receive this amount of money. Okay, so that's it for CDSs. We are not going to cover this part here. I will continue the topic of credit derivatives in the next video. Thanks.